who's a forensic specialist for CERT US.
Stand by. Forensic specialist, but evidently not the PowerPoint specialist. All right, that's good. All right, hi. Thanks. Sorry about the late start. Thanks a lot for joining me. I know that there's a very trendy iPhone demonstration going on next door, so I appreciate it. Thank you. All right. I'm going to be talking about what I'm going to just refer to as difficult data acquisition, the general title. Subtitle is going to be how you build your own password cracker in 15 minutes with a disassembler and some VM magic. We'll do that towards the end of my talk. First, I'd like to get a little background, just a little background about CERT. You guys probably know it, or most of you hopefully know it, as a place that publishes vulnerability reports, that runs something called the CERT Coordination Center, which helps set up and coordinate international CERTs, computer emergency response teams at the national level across the world. It's a U.S. government federally funded research and development center, which makes it sort of like a national lab, like Sandia National Labs or Lawrence Livermore National Labs. Our focus for research is information security. We're housed at Carnegie Mellon University in Pittsburgh, Pennsylvania, which is very convenient since Carnegie Mellon has some excellent IT resources. And we also have a forensics team, which I'm on. We do work mainly for law enforcement and other government security agencies. We're not pure research. Our work is split about half-half between R&D, research and development, and what we call operational support. Research and development, we're not a huge team. We're not a big software house. We focus on developing tools and techniques that meet what we see as gap areas in the current forensic practice, forensic community of our customers. So we're talking mainly law enforcement investigators. And we try to fill some gap areas in existing tools that they don't fill. We also provide some training in how to use these tools and distribute these tools to the law enforcement community. And we have some publicly available tools too. I'll highlight one later that's open source and widely available. The other half of our time is spent doing analysis on a case-by-case basis with law enforcement agencies. We have the two major U.S. Federal agencies, the FBI and the Secret Service, both have liaison officers that are housed full-time at CERT, and so we work closely with them. And we have done acquisition support as well. We do an increasing amount of acquisition support. Basically means accompanying search teams in order to help acquire data from systems that are being searched if there's any indication that those systems are going to be difficult or tricky. So, in case it isn't clear by now, I'm speaking from a perspective that might be a little unusual at the conference. I'm speaking at it from the perspective of a forensic investigator. So when I talk, try to keep that in mind. Hopefully it'll be a refreshing change. If I make references to legal stuff, it'll probably be based in U.S. law, which is what I know the best. All right, so much for the perspective and background. I think this is an incredibly exciting time for forensics, for forensic analysis, for forensic investigators. There's a rash of new tools and techniques that are blooming. We've seen some very sophisticated techniques using JTAG access ports and custom-made harnesses to grab information from embedded devices, to grab data straight off flash RAM chips, and to then be able to use, for example, the wear leveling translation tables inside those flash RAM chips to create a nice history of data deletion and data creation on that flash RAM chip. Stuff that you can't see actually at the device level. The big mainstream forensic platforms are likewise making some amazing changes. They're both moving towards a distributed processing framework, which will allow them to handle the multi-terabyte sort of sets of data that we're acquiring, are becoming very common to acquire, in fact, and live forensics and memory-focused analysis, which we've seen. Actually, yesterday, Peter Silverman gave a very good discussion about Mandiant's new tool for reconstituting processed memory space from a physical memory dump. Stuff like that makes this really, really exciting. We're extracting a good deal more, finding a good deal more data to analyze and extracting a good deal more. And that's great news. But there's one area that hasn't moved at quite the same pace and is actually creating a rising and very daunting challenge for law enforcement in particular, and it hasn't been addressed by any of the advances I've discussed. And I'm going to be talking about that area mainly at this presentation. So what that is acquisition, basically seizing, grabbing data, grabbing what you want to analyze. There's several problems that are becoming increasingly significant in this area. The biggest one is pervasive encryption. So it used to be that if you were talking about sophisticated computer criminals and trying to acquire data, trying to search their computers, trying to seize their computers for evidence, it wouldn't be much of a surprise to find that some form of encryption was being used to protect probably what you wanted to see. But increasingly, this is becoming quite common across the board. We're seeing this in criminals who are using computers as a simply ancillary component of their activities, right? Even just for email, right? These guys are becoming increasingly aware that that they've got stuff they want to hide and to use encryption to do it. Another thing that's going to become somewhat of a problem, although not of the same scale, is the ability to bind hardware devices using a TPM, using the TPM chip, so that you can't sort of rip a hard drive out of a computer and get it to work on another computer, or at least not easily. There are some other countermeasures. I'm going to show you some pictures of some cute ones. But the thing that's really, perhaps it's going to surprise some of the people in the room, these trends are creating a serious problem for law enforcement in that they have to change not just the technology that they use to acquire data, but they have to change the entire sort of vertical chain of related events that law enforcement need to succeed. They have to change their legal framework, and you could go on for a long time about this, but just one area is search warrants, right? Everybody thinks of search warrants as what you see on television with people kicking a door in, SWAT team runs in, everybody freezes right down on the ground. Actually, that's called a no-knock warrant. A very, very, very small percentage of warrants in the States are no-knock warrants. And in fact, in computer crime, they're exceedingly rare, or have been up till now. There was the federal district in the West Coast, responsible for the Silicon Valley and San Francisco, had not issued one no-knock warrant for a computer crime till about a year ago, till about last October, in fact. And it was a big deal when it did write that first one. And it was also very important, by the way. It made a big difference in being able to seize the data. And so that's actually helping change the way courts are looking at this. Tactical issues, right? So the team that goes in, the entry team, is not the forensic analysts. I can assure you when they go into a building, they look very different from me. As a result, these guys are primarily focused on officer safety, on making sure that the building's secure, and making sure that other people in the building aren't harmed, and for traditional sort of evidence destruction, so guys flushing stuff down the toilet, right? Now they've got to be aware of all the subtle ways that data can be destroyed, because data is their evidence now, and to be aware, figure out ways to stop it and keep that in mind when they go in. It's a big change. It's actually a really big change for law enforcement. And finally, there are technological changes, which wouldn't surprise anybody, and we'll talk a little bit more about them. So I've already mentioned some of this. Encryption is becoming a lot more common, as I said, and for the reasons I've said. we're not seeing much file-based encryption anymore. Instead, it's being edged out by full disk encryption or container-based, right? So like the old style TrueCrypt also still does it, but the TrueCrypt where you take a big encrypted container and then you can mount it as a volume and unmount it very rapidly. So what this means for forensic investigators is that recovery is going to be all or nothing, more than likely, right? You're either going to be able to get to that system and get access to a container that's mounted or a disk that's on a running system and therefore decrypted, or you're probably not going to get anything unless you can somehow get the passphrase. That means access to the live boxes becomes critical, and that feeds back into what some of the other changes in the acquisition process I've talked about. In the two most recent cases where we were on hand to help with acquisition, both federal, both multi-site searches, so there were dozens of systems seized at the same time at multiple locations. Every single storage device that could have contained evidence or did contain evidence that was of interest, it was used for anything interesting in this organization, had full disk encryption. Most of them had multiple layers of countermeasures, but every single one was full disk encrypted. That's, I mean, it's an anecdote, right? It's just two cases, and they were fairly major, but that's an indication of what is coming down the pike. And here's another indication, TrueCrypt downloads. Well, that's not too surprising. These are cumulative downloads. There's now more than 7 million TrueCrypt packages that have been downloaded. A lot of them are replacements, upgrades from version to version. But as you can see, the curve is steepening. We're getting an increased use. And for those of you, I'm sure everybody does know, but TrueCrypt's a very popular open source, probably the most popular open source encryption application. Now, here's some less likely that you know countermeasures. Anybody here know what a RASCAT is? Anybody ever seen one? RASCAT is an electromagnetic field generator, right? It's like a giant degausser, or not giant, it's actually about this big. You can see it. There's one picture up there that shows it embedded inside a computer case. There's also a backup battery for this. They think this through, so you can't pull the power plug on the computer and disable the RASCAT. It's made in Russia. You can buy it from eraser.ru if you're interested. You can trigger, there's an external unit, the white one in the middle of the frame there. You can trigger it with a little key fob, like a car alarm key fob, car opener remote. And it'll generate an electromagnetic pulse that will basically wipe your disk for you. It'll make it unusable, in fact. Some folks had it looked at by the Seagate people. Seagate has a research lab in Pittsburgh, and they tested it on a number of their drives and found that, yeah, it's very effective. Another thing they like to do is booby-trap the case. So when you open the case to try to get to the hard drive, boom, it triggers the RASCAT. They've also got proximity key fobs. These things come in different shapes and sizes. I've just got one displayed here. But when you move more than 6 to 12 feet from a computer and you've still got the key fob on you, it can trigger a variety of programmable events in the computer, from locking it to dismounting your encrypted containers to shutting it down. Pick your level of paranoia. So these are all considerations right now for when you're setting up a search, when you are arresting somebody or trying to facilitate a search, the scene. So, that's a good echo. That's your best case scenario. That's what I like. Right? If you walk into a room, this is a hotel room in case you couldn't tell, and there's a giant panel antenna sitting on top of the lamp. And a couple of computers running, they're unlocked. You've got probably at least one felony on each screen as you walk in. That's actually a really interesting situation because you've even got Evian there while you wait for the disk to image. That's really nice, right? You can't get better than that. On the other hand, something along this line is actually more common. Now, that computer monitor looks like it's on, but that could just be a big grease stain. And I guarantee you that everybody in that room is going to be using 3 pairs of latex gloves just to go through that trash. Yeah, it's there. All right, but the technological adaptations that we're seeing that need to be implemented, I guess, for dealing with the countermeasures that I've discussed, in particular encryption now, because you can't, RASCAT is a lot harder to deal with. We're seeing acquisition procedures change, right? The traditional, until actually very recently, most law enforcement departments would approach a running computer as if it were a problem, right? They would see a running computer and it would be like, ah, and then they'd have to pull the plug on it because, after all, you want to preserve the state of the disk. And that was the standard MO for police acquisition. That's obviously pulling the plug now is going to give you very little when there's an encrypted drive. So that for one has changed and is probably going to no longer be the case. Increasingly, running systems, the first step that's being used if you have interactive control is to run tools to screen for encryption. CERT makes some that are very effective at determining whether or not you have full disk encryption in place, whether or not there are encrypted volumes mounted, what's going on in the system. And when in doubt, increasingly also the norm is taking a live image of the computer disk, right? Grabbing memory, usually a full physical copy of memory. But that's if you have interactive control, right, which we don't always have. If you don't have interactive control, then it gets really interesting. One of the things that you have that the average attacker of a computer system would not have is physical access, right? You're in the room with the computer, by and large. If you're serving a search warrant, I hope you're in the room with the computer. So you've got physical access you can leverage. In the case, if you want to, and the computer's running, and you want to get, say, a memory dump, you can use FireWire, or plug in a PC card and use FireWire through it. That's thanks largely to the work of Max Dornsief and Adam Boileau, who've figured out a lot of neat stuff with that. You can also, if there's a network in the environment you're searching, you can harness the fact that very often internal networks have some higher trust level, and you can get on the network and harness that trusted status to perhaps escalate privileges. And finally, you're looking at exploiting vulnerabilities on the box, on your target system, and you're looking at services and applications that may be vulnerable. Sounds fairly natural, I'm sure, to many of the people in the room, but you've got to think, again, from the point of view of law enforcement and from the point of view, in particular, of courts and lawyers, that now they're going to have to figure out a way to introduce as evidence stuff that you hacked into a box to get, right? Like, wait a second, what did you do again? But you see where this is going, right? Because of these countermeasures and because of the change in the environment, increasingly gaining access to gain evidence is going to look a lot like the stuff that computer crimes are made of, breaking into computers. It's also going to require new skills. So acquisition team's going to become more specialized. Now, this probably isn't as, in and of itself, isn't as unusual as you'd think, right? When police discover a large safe in the corner of the room, it's locked and nobody's going to give them the combination, there's no problem calling a locksmith in, having him break into the safe. That's standard procedure, and it doesn't really harm evidentiary. I mean, that's been accepted nicely in courts. It's not a problem. But it is something they're going to have to think of now in terms of computer acquisition. And it's only going to probably get worse, right? It's just like the arms race in the broader security sphere. As the incentive, as investigators get more skilled at defeating these defenses, the defenses themselves will get stronger. So you need a little bit of flexibility. You need to be able to use very sort of ad hoc methods, adapt methods to what you see at the time, and some offensive skills. Now, these are definitely not qualities that are emphasized in the forensics community. The forensics community is built on doing things the exactly accepted way, the practiced way, the way that's been already succeeded in court when you've admitted evidence. And so it's a big and will be a wrenching transition to start incorporating these sorts of techniques into the acquisition process. All right, so what I'd like to do is run through a quick scenario just to demonstrate what this might look like. This scenario is actually based on a real-life case, about a year old, again. It's just based on the case, so there will be some important differences. But this case, we've grabbed physical memory from this box. So we came in, there was let's just assume we've all entered a room. Assume you see there's a running computer, it's locked. You have a FireWire port, yay. You can grab access, you can grab physical memory from the system with FireWire. Discover that the system is full disk encryption, in this case, best crypt volume encryption. So you've got a disk image of an encrypted disk, right? You've got an image of memory. What do? What's next? Well, if you have memory, the good news is you have the key, right? You have the key that's used, that Bscrypt uses to encrypt the drive. It's somewhere in memory. It'll be in kernel pool memory, actually. And you can extract it and decrypt the drive. Yay! But you can do perhaps something a little more, or you could have, and we did a year ago, and that is you can get something a little more valuable from memory. What's more valuable than the key to decrypt the drive? Any guesses? How about the passphrase? Why is the passphrase more valuable? Well, it tends to be used, passphrases tend to be reused, and if they're not reused, they tend to give you insight into how passphrase how the other passphrases that are used might look, right? What they might look like. So a year ago, it was pretty much the case that every full disk encryption application was really good about cleansing memory from once you entered, if you entered a passphrase and it needed it to decrypt or to access the key material container, it would then scrub the passphrase from memory as soon as it was done using it. But until a year ago, most of the applications forgot one critical thing. So when you boot into a full disk encryption environment, you've got a pre-boot authentication phase, right? Sort of like roughly where your BIOS initialization screen it transitions right into this little environment where it asks you to enter a passphrase. When you enter the passphrase, you're still in that environment. And then control transitions to the operating system, and off you go. What the full disk encryption vendors didn't realize was that there's a BIOS keyboard buffer that none of them wanted or realized to clear. That's roughly, it starts at hex 41E, if you take a linear look at physical memory. It'll hold 16 keystrokes. Actually, what it holds is the ASCII keystroke and then the scan code for the key that was pressed on the keyboard interspersed. And it will wrap. It's a ring buffer. So there's a pointer to the head and tail. This has actually been known. So can you see? You can probably see in there, right? What was typed here. This is. You have to sort of skip every other character because every other one is a scan code, but it says, "Hi there, HITB!" exclamation point, right? So this has been known for about 10 years, right? There have been disclosures and grumblings on lists about how initially it was mainly a concern for the BIOS password, right? Not full disk encryption, more modern. But it's been rediscovered again and again. In 2005, as it directly pertains to full disk encryption packages, there was a couple of vulnerability reports in 2005 I've cited there. There's one just earlier than this year, and the one that was reported this year named a bunch of vendors, and as a result, I think it's gotten a lot more attention. So the bad news is, remember I was talking about the arms race? Well, bad news for investigators is, a year ago, you could recover the passphrase from that area of memory for practically every full disk encryption application. Now, you can do it for, if you're lucky, maybe there's half of them that do it. TrueCrypt, when it launched its full disk encryption package, was very careful right from the start to scrub that space. Bestcrypt has started doing so as of a few weeks ago when it released version 2. Latest PGP does reportedly. Pretty soon this hole is going to be closed completely and we'll have to move on to different methods. But let's go back to the scenario. So we're back in our scenario. What happens if we've got a passphrase that we've extracted from memory, from this BIOS keyboard buffer, that's longer than the 15 characters that can be stored there? Well, I mean, it's a 16-character buffer, but the last one's always going to be return. So it's 15 characters, really. And in fact, a year ago we did. This was, what you see there was what we recovered from the buffer. E-A difference, exclamation point. That was the last component of this guy's passphrase. Well, that could be B a difference, C a difference, R a difference, I am a difference. No, it wouldn't be I am, but anyway. Make a difference, take a difference, fake a difference, fake a difference. There's a bunch of stuff. I mean, what we ended up doing is having to create a very lengthy list of possibilities, scripting it out. But then you've got another problem. There are no commercial password crackers that handle Bestcrypt volume encryption, right? So what do? Well, you can actually make one yourself, but when you do it, you've got to keep a few things in mind. One of the most important ones, and this is one of the ones that's the hardest to get around, is that usually it's time sensitive, because if we're talking about material that was seized during a search, there may be a very big difference between what crimes can be charged, the individual can be charged with, or the group can be charged with, if you recover this material than if you don't. Right? So it makes a fairly large difference, even very early on, because you have to be charged quite early. And the other thing you have to keep in mind is that whatever we do, it has to be something that you can demonstrate in a court of law provides forensic quality evidence. That's not that easy, but again, it's not that hard, but again, it's something you have to keep in mind. So for this, what we'll do first is we'll use LiveView, which is the tool I mentioned, or the tool I mentioned earlier that's publicly available. It's available via SourceForge. And we'll take our disk image, the image of that encrypted drive, which is just a bitstream copy of the content of the encrypted drive as one big file. And we'll virtualize it. We'll create a VM around it. So that's what LiveView does. And it does it very well, actually. And if you've got a unencrypted Windows machine, LiveView will do a lot of massaging to the machine, set up the hardware for it so that it will actually boot up nicely within the VM environment. Has anybody in the room seen LiveView before? It's widely available. The URL's there. There's a law enforcement version that isn't widely available, but c'est la vie. So what we do here is basically just use it to create a VM that we can use based on that encrypted drive. And then, once we've done that, once we've done that, we've got so the VM will let us play around with that disk. And the one thing that LiveView does really nicely is it will create, it uses VMware's disk snapshotting feature, which means that if you've got a working copy of the evidence that you don't want to keep copying again and mess up, LiveView will create what's effectively a diff file, a separate file to which all the changes to that disk are going to get written. And so that gives you the ability to use, a nice working image that you don't want to change and you want to preserve, and still change the state of the virtual machine. Right? So now we're going to get the best script rescue disk. Now all of the full disk encryption packages have some form of rescue disk in case the boot sector is damaged or for some other reason you need to repair or decrypt their disk, the encrypted drive. Now, why are we picking the rescue disk? Well, for one, there's a better forensic outcome. Remember, well, actually, it's easy to understand. If you, from the rescue disk environment, directly decrypt the entire drive, you've never booted into the operating system again. So what you have decrypted and what you therefore can now image and present and start looking through as evidence has never been booted since the acquisition time. So you're not changing timestamps, you're not changing other stuff that you would change if you had to boot into the system first and then decrypt it. There's some other reasons too. One is there are less anti-reverse engineering techniques employed in the little decryption engine. It's a tiny little lightweight engine in the rescue disk. They don't protect it, they don't care about it that much. It's real easy to modify. And there's some limitations too to working in that environment. It's always a trade-off. Let's see if we can take a look actually at that. Everything's up and running here. All right, so here is a virtual machine. So there's a couple of bits of this demo that are like pre-baked. I've already got a virtual machine. I didn't bother creating one from a disk image. Let's first just verify that it's encrypted. We'll just fire it up. Won't take a second. Hey presto, yep. And that's not the password. Okay, so it's encrypted. Now, let's see what happens when we attach. I'm attaching a floppy drive. Usually rescue disks are ISOs, or CDs. They're designed to be burned to CDs, and in fact, that's probably the preferred method. But you can typically extract, it's easier to work with floppy. You can work with either. It's slightly easier to work with floppies. That's why I'm working with the floppy image I've extracted from the CD and just created a floppy. So here with that set to boot, this is what happens when you boot into the rescue environment. All right, you get recovery utility. Do you want to continue? Yeah, I'd like to continue. All right, it finds that there is an encrypted drive. It recognizes it. It recognizes the rescue disk in this case has a little recovery packet on it that contains information about that installation, and it recognizes that they match. So, all right, we're ready to go. So let's just guess. In fact, I'll type guess. Oh, that's not right. I'll type guess 1. That's not right. I'll type guess 2. Uh-oh. We get 3 tries. That's going to take us a long time if we've got, as our password list right now, just one I threw together, has 10,761 entries. That's going to take a very long time. And besides, we don't want to sit here typing, right? We've got to figure out a better way around this. All right, let's go do that right now. So, what we'll do, all right, what we'll do is have to get back into the environment I was in here. Okay. Sorry about this. Okay, we can mount that rescue floppy and take a look at the programs that are on it. All right. Okay, so you've got, well, the standard sort of DOS boot disk sort of components, right? Command com. You've got rescue.rsc, which is the little packet file that is mated to that particular encrypted disk instance, and a couple of recovery programs. Well, the one that was run initially it was called recovery exe. So let me just copy that. To my desktop. And then let's see what we can do with it. Let's take a look at it. Ooh. By the way, if anybody has questions that they want to fire up, I don't mind answering them in line here. Let's see if we've got this now. There it is. All right. Now all we need is IDA, our disassembler. And if anybody wants to start a stopwatch, because I did say 15 minutes, didn't I? So you can go ahead and do that. All right, so we're using IDA. I, again, am assuming most people in the room are familiar with this exceedingly excellent tool. Wow, I'm having a hard time. Let's do this, okay. And I'm very lazy. A lot of people are very lazy. I'm very lazy. I'm not going to worry about following execution flow all the way through this. I'm going to look for the string that tells me you've entered the wrong password, because I know somewhere around there it's going to have to update the count of how many passwords I've entered, so that it can then tell me to go away and drop out. Right? So the first thing I'm trying to address, so I see the string and I see where it's referenced. We go to that function. Let's actually switch. Let's move this out of the way here. So password you've typed is incorrect, right? And then right after that, you can see, after you enter an incorrect password, we increment the DI register. Then you compare that register to 3. And if it equals, or unless it's less than, if it's greater than or equal to, it'll jump you out, right? So that's very easy. That's an easy fix. That's, in fact, let's go to text view. Where are we? Okay, and I'm going to do something a little odd here just because I think it's easier to demonstrate. I'm going to open also in a hex editor side by side, even though we've got a hex view in IDA. So where are we? Let's go back. There's that. All right, we're not synchronized, are we? Why not? Anyway, well, I can tell you, let's just go back here and work on it, right? I can tell you that we are at 8E3, and increment DI, right, is the opcode for that we'll see when we go to 8E3 is, anybody remember the opcode for increment DI? Yes, 47. So the first thing we'll do is NOP that out, change that to 90, a no op instruction, which will tell the processor not to do anything. And that means the next time the counter is never going to get incremented, right? So now you've got an unlimited number of password attempts. Boom. 1 byte, change, byte patch, save the executable, throw it back. You're okay. But we want to do a little bit better. Because you know, we saw when you type, all you see is asterisks, right? And I think we can do a little bit better than that. So what we're going to do now is find, in fact, where those asterisks are entered, right here. You see, you just push the asterisks onto the stack, then you call put on the screen, put char. And what we'll do now instead is, again, try to go we'll patch this out, and instead of putting, if you'll notice in the previous instruction, what's happening is the character is being stored in the AL register, and then is being pushed into this string that's holding the passphrase, right? In this case, we're going to take the fact that the character is still in AL and push that back onto the stack, and then that'll get printed out. So again, we can actually, the really nice thing about this is we can actually byte edit in place with a hex editor and not have to do anything more complicated or elaborate. So now that's 2 instructions. It's at 884. All right, so let's go find it. 884. I hope that's these 2. Yeah, 2A, right? 2A was the... Okay, so what we'll do is the first instruction, we're only going to replace it with a single instruction, which is to basically push AX. And that is 50. So there's a single opcode there. So now let's save this file as, let's call it something else. Let's call it special. Okay. And we can close this. And then we can start putting this back into our password, into our virtual machine environment, and actually use it as the cracker we need. So let's see. Let's hope I've done this correctly. I was a little fast and sloppy there, but let's see. All right, and then I should also have a password list set up here. I do, so I'll copy password text. All right, so let's just make sure we've got everything in our little floppy environment, the little floppy image that I mounted. Yep, we've got the password text there, and we've got special.exe. Right? So now we can unmount that. Puppy. And let's go back into our VM environment and fire up the encrypted, the virtual machine based on that encrypted drive. Okay. We're not going to continue with recovery exe because we have another program. And the nice thing is it just drops you a DOS shell, right? It's a DOS bootable disk. It drops you right there. We're going to instead do special. Well, let's make sure that everything here looks good. Yeah, special's there. PW text is there. So we're going to do special exe and angle bracket PW text. And let's see what happens. So what I'm doing here is just directing a standard input, my password list, right, into as standard input to the program. Now, the one trick I have to do is the first password, or the first thing in that list has to be a Y, because you've got to answer the question, do you want to go ahead, yes or no, right? But once you've done that, one password you want to try per line, or passphrase per line, and let's go. There you go. So now we're trying to break into this machine, and as you can see, you should be able to see, there's, oh yeah. Yeah, you can see it's all in plain text, right? We've managed to produce, and we found the password, right? Which is tester 123 in this case. It's not the password in the case a year ago, but it's working. So now, what's happening is we know the password. The disk is being decrypted in a method that will be easy for us to explain when we try to take it into court. We've used, Your Honor, we use the recovery program supplied by the manufacturer of the drive, of the encryption application, to decrypt the drive. It was never booted, and this is why we have confidence of the following evidence, da-da-da-da-da, right? So a couple of little things to keep, or that would be good to keep in mind on this. Like that password list had only 10,000 or so passwords in it. We didn't run through all of them. I put it onto a floppy, right? How much room do I have in a floppy? 1.4 megs. If another nice thing about using a VM environment is that most password lists that you're going to try are going to be a lot bigger. No problem. You can just attach a virtual drive to the machine, boom, copy your password in there, and then that's what you angle bracket into your cracker, right? It's really easy. And you can create multiple instances of this virtual machine if you want to parallelize the task, right? Because I've got to say that the environment's not, I mean, this is not as fast or as slick as a real, purpose-made password cracker or any of the commercial packages out there. But it's doing the job, and it does it, what else can you want, right? So that's, that's how was anybody timing that? Did I do that in under 15 minutes? I hope so. No reason why I shouldn't have. And that's the other important thing. We did it fast enough that now, if you've come back, you've had enough time to generate a password list based on, say, stuff you recovered from the BIOS keyboard buffer, if you were lucky. You could really run through this in the course of that same day and have some answers by maybe the next day for prosecutors or for other investigators who want to know about what's on the drive. Well, you can now tell them. Let's see, where am I? On here. Give it a second. Okay, let's not give it a second. Let's go where I want to go. Okay. All right, so yeah, that's how you can build your own password cracker in 15 minutes with a disassembler and a little VM magic. So I'd like to take some time to thank Dylan and the rest of the HITB crew here for helping out. Thanks, CERT, for letting me come out here. Took a little bit of arm twisting. And now I'd like to throw this open to questions. Does anybody have any questions about this particular thing you've seen or about anything else of interest I might know about? Be able to talk about.
Hi, I'm interested. You said that you were able to get memory dump from FireWire.
Yeah.
How do you actually do that? Now, let's say I've got a disgruntled sysadmin. He locks up everything, he encrypted stuff, and I quit and walk out the door. And I have a database
Oh, wait, are you the city of San Francisco?
No.
They had that problem just recently, but go ahead, yeah.
Yeah, but the San Francisco case was just, I think, a very good example.
Yeah.
And it went to press. I'm sure there are a lot of other cases like this.
Quite right, yeah.
And now, let's say I have someone like this, and he just walks out the job, encrypts stuff, and I have a very, very important, some really important stuff in there, and he has locked the desktop, or I can get to it, and I'm afraid to actually reboot it. How would I get stuff off the memory? Is it using FireWire?
Well, you see, it depends, right? The desktop computer, if it's a typical corporate installation of a desktop computer, it's unlikely to have a FireWire card. Now, sometimes some motherboards will have FireWire, essentially a FireWire bus built into them, but they haven't, that particular model hasn't activated it, so you could try to hunt around you could basically look up the motherboard specs and see if there's a way to hook into that. If you're lucky enough to have FireWire, though, Adam Boileau released a tool, 1394 memimage, I think is the name of it, that it does a couple of nifty little tricks. I think they've been talked about in other forums. One of them is it will, for Windows systems won't set up direct memory access, DMA access, to another computer by default. So you have to pretend to be a device that requires DMA. Adam used iPod because he had a great sense of irony. So you're running a Linux box, you fake You set up your CSR, the little config ROM register to say, I'm an iPod, and then you plug into a Windows machine, it gives you DMA, and you copy memory. It's, it's that easy.
Perhaps we can continue on offline.
Yeah, that's fine. Yeah, no, I'd be happy to. You know, I think I started a little late, so although there's still 10 minutes on the clock there, unless there's, maybe we'll just see if there's an urgent question or something that I was really unclear about, I can answer it now. If not, I'll be hanging around here for the rest of the day, and you can come find me. And that way, maybe we'll get back on schedule if I just wrap up now. Thank you all. Thanks, guys.